I'm member 1 from Good Hash. My name is Nim Xiaowei and my matric number is EFT1083. So we are here to present a project title is Application of Derivative of Event or Scope in Jeli campus from course EFT1083 Basic Mathematics. So we are choose a scope and the scope is Jeli campus leg. So this is my question. The problem is the leg is a rectangular leg. Rectangular leg located at the heart of the university campus. The length of the leg is fixed at 200 meters but the width can vary. The university wants to construct a fence along one side of the leg perpendicular to its length and using 300 meters of facing material. So what should be the width of the length to maximize the enclosure area? To maximize the enclosure area, so we need to optimize the width of the leg. So we can denote that the width of the leg as W in meters and the length as L, which is fixed at 200 meters. So we can get a equation such as this. So we can express the area as a function of the width and then optimize it to find the width that maximizes the enclosure area using the derivative. So the area, this can be rewritten as this. And to find the maximum of A, we take the derivative of A with respect to W and set it equal to 0, just like this. And setting dA per dW equal to 0, like this. And we can get that the equation has no solution, including that the derivative of A is always positive and there is no maximum value. So therefore, the area A increasing indefinitely as the width of the leg increase. In other words, to maximize the enclosure area, the width of the leg should be as large as possible, limited only by practical constraints. Hence, the width of the leg can be made arbitrarily large to maximize the enclosure area given the consider of using 300 meters of facing materials. Okay, so like this. This is all my presentation. Thank you.
Hi, my name is Nakilom Pidawat and my matric number is F2280018. I am member 2 from group H. This is my question. UMK Jeli Campus Lake is a man-made reservoir that supplies water to the campus. The lake is initially empty and water is being pumped into the lake at a constant rate of 5 cubic meters per minute. The water level is rising as a function of time given by the equation Ht equals to 0.02 T power of 2. H represents the height of the water in meters and T represents the time in minutes. Determine the rate of which the water level is changing when the height is 10 meters. This is the solution. To determine the rate at which the water level is changing, we need to find the derivative of the given function Ht with respect to time. This will give us the rate of change of the water level with respect to time, also known as the derivative of Ht with respect to t, denoted as dH over dt. Taking the derivative of Ht with respect to t, dH over dt equals to d times 0.02 t power of 2 over dt. Applying the power rule of differentiation, we get dH over dt equals to 0.04 t. Now, to find the rate at which the water level is changing when the height is 10 meters, we substitute h equals to 10 into the derivative dh over dt and solve for t. Now we substitute this value of t back into the derivative of dh over dt to find the rate of change. Hence, when the water level is 10 meters, the rate of which the water level is changing is approximately 0.8944 meters per minute. That's all for me. Thank you.
Hi, my name is Launi binti Muhammad Syarif and my number metric is F22A009. I'm member from group H. The question is UMT Jeli campus lake is a reservoir that collects rainwater from the surrounding area. The rate of which water flow into the lake is given by function RT equal to T power of 2 minus 40, whereas R represents the rate of water flow in cubic meter per hour and T represents time in hour. Determine the maximum rate of water flow into the lake and the corresponding time. The solution is, to find the maximum point, we can take the derivative of RT with respect to T and set it equal to 0. This will help us locate the critical point where the maximum occurs. Taking the derivative of RT with respect to T. Setting the R divided by dt equal to 0 and solving for t. Since the second derivative is positive 4, the function is concave up at the critical point t equal 1. Therefore, this point represents the maximum. Now, let's find the corresponding maximum rate of water flow. Substituting t equal 1 into the original function RT, and the answer is negative 2. Therefore, the maximum rate of water flow into the lake is negative 2 cubic meter per hour. Note that the negative sign indicates a decrease in the rate of water flow. The maximum rate of water flow into UMT Jeli campus lake is negative 2 cubic meter per hour and it occurs at 1 hour.
I am Amir Fizuddin bin Muhammad Faisal. My number metric is F22A0190. I am member 4 from group H. Problem description. The UMK Jeli campus has a beautiful lake beside the mosque. The university wants to construct a walking path around the lake. The shape of the walking path is a circular ring with an inner radius of 20 meters and an outer radius of 30 meters. The university wants to determine the rate at which the area of the walking path is changing with respect to the change in the outer radius. To find the rate at which the area of the walking path is changing with respect to the change in the outer radius, we need to differentiate the area formula of a circle with respect to the outer radius. The area of the walking path is given by the differentiate between the area of the outer circle and the area of the inner circle. Area of the walking path equal area of outer circle minus area of inner circle. The area of a circle is given by the formula A equals pi times 2, where A is the area and R is the radius. For the outer circle, the area is A outer is this, and for the inner circle, the area is A inner is this. Therefore, the area of the walking path is area of walking path equal 900 pi minus 400 pi pi equal 500 pi. Therefore, the area of the working path is. Now, to find the rate at which the area is changing with respect to the change in the outer radius, we take the derivative of the area formula with respect to the outer radius. D times area of working path over dr equal D times 500 pi over dr equal 0. Since the radius of the outer circle is changing, we differentiate the constant term 500 pi with respect to the outer radius r, which result in 0. Hence, the rate at which the area of the working path is changing with respect to the change in the outer radius is 0. This means that decreasing the outer radius of the working path does not affect the area of the working path. Thank you. So that's all from us. Bye bye.
Bye.
Swipe up.
Bye.
Sit down.
Shoo!